So, this should have been fairly easy. One of the productions of a lambda calculus expression is a list containing two lambda calculus expressions. So you could have x followed by, let me put that closing one in there, a lambda xx. This x occurs bound, this x occurs free.
Something else.
Well, you could write it a zillion different ways.
No, I mean, in parentheses after y in there, would it still be?
If you put y here,
Yeah.
no, because now this x occurs free. It's not bound by this x. That make sense?
I'm still kind of having difficulty
With who?
with the difference between bounded.
Okay, so
We can go over it later.
yeah, well, so first of all, I mean, it's important to what we're talking about right now. So understand that variables being bound is equivalent to us writing a method where we have local parameters coming into the method, those binding variables that we have access to in the method. So if we were writing this in Java and I said something like void blah takes an int a as a parameter, inside of this method, a is bound. We have a variable in there that is bound by this definition of it. So think about what a lambda calculus expression is. A lambda calculus expression is an unnamed function, unnamed method. So this guy right here might be the value of this guy, this function. Instead of being called blah, we've given it no name. So the equivalent here would be define blah to be a lambda that takes in an a, and then anywhere inside the body of that, a would be bound. That make sense? So in this case, we have, so given my potential solution here, one of our productions for a lambda calculus expression is a lambda calculus expression followed by a lambda calculus expression. A list, a two-list of two lambda calculus expressions. One of our productions for a lambda calculus expression is just an identifier. That's our identifier. So here's our variable x. That guy occurs free all day long. He's not even inside of a production where a binding can happen, right? The only place where a bindings can happen, like we talked about last time, is inside of a lambda, inside of this production, production number 2 of our lambda calculus expressions. So all bindings, 100% of them take place right here. Make sense? Okay, so this guy, 100% of the time, that guy occurs, because I see an x, and he occurs free. That would not be an example of x occurring free. It's true that in this first lambda calculus expression, x is not bound, but x also does not occur. Make sense? So in this case, x occurs, and it occurs free because in this scope, it's not bound by anything. So we're really talking about the scope of a variable. And when we talk about lambda calculus expressions, we're talking about the scope of a variable specifically associated with functions.
You have more than one variable bounded by the thing, right?
Not in our current definition. Current definition says a single identifier. If we go back here, and so we have one identifier right there. Pretty quickly here, we're going to be evolving that to be 0 or more identifiers. But we're still dealing with the easy, trivial version of this. So it's going to get worse. All right. But the good news for us right now is when we write code, we can assume that there will always be exactly one. As far as right now goes, we are not allowed to have 0 variables bound. We have to have 1. Not 0, not 0 or more, exactly 1. Yeah.
How do you pass arguments if you have 0 identifiers?
How do you pass arguments if you have...
Like into the function when you're
Okay, so how do you... I guess I'm not understanding the question. How do you pass arguments to a function that takes no parameters?
Right.
That doesn't make sense. How would you call a function in Java that takes no parameters? you would call it, but you wouldn't pass in any parameters. So if you try to shove a parameter into something that takes no parameters, it's going to be very unhappy, right? So I guess the short answer is you can't. So if I have, you know, let's just kind of go over here to scheme and look at this. Let's just get rid of this crap. Okay, so for instance, let's say, let's just run this. Let's say that I have a lambda that takes an x, and this guy returns x times x, something like that. All right, and I want to apply this to a 5. I get my 25. So that production there is this is a lambda calculus expression followed by a lambda calculus expression. That's that version of the production. The first element is this guy right here. That's my first lambda calculus expression. My second guy is this guy right here. What your book's going to later call this is an app expression. It ends up giving a name to that third production of our lambda calculus expressions. That is an app expression. That is to say, this is a function, and that function is being applied to this parameter. Does that make sense? So this 5 is being passed in as x, and then we're multiplying x times x, boiling down to a 25 in this case. Okay. Your question though is, how do I do this? Here's first, this is wrong all over the place, right? So let's just force this to be a -3 or something like that. So here's a function that takes no parameters and just boils down to -3. This is literally a huge roundabout way of getting to the literal -3. Useless function, okay? But technically it's still a function. This is a function that takes no inputs, 0 parameters. So if I try to pass 5 to this guy, expects no arguments, but found 1. I tried to shove a 5 in as an input to something that takes nothing. Was that what your question was? Is how do you...
Well, I thought like the identifiers were the arguments.
The identifiers are the expected inputs. So this guy expects a single parameter that I happen to name x here. So I can now pass it a 5. I don't have to use x over here. So in this case, x is bound, but it doesn't occur. So I could pass 5, 14, 2008, the list ABC. I could pass whatever I want to this guy. It'll come in as a variable name x, of which I'm not even using, and just boiling down to -3. That make sense? Okay, so this is the expectation of a parameter. So this guy is your variable name that captures this value in this example. So x will equal 5, and then what I do with that value, this is the body of that function. Just like the body of a method in Java. Yeah.
So maybe I misunderstood or misheard, but you're saying that where x is right there, I can only put 1. You're saying we can only have 1.
In our current definition of our lambda calculus expression, this guy, this definition that we're operating off of for all of our
But like for all of the homeworks, we've used more than 1.
we're schemes lambda expression can take in many, 0 or more, right? For our assignments that we're using, when we're writing stuff to manipulate lambda calculus expressions, the assumption right now is that they take exactly 1 input. Okay, because things start getting more complex when you start allowing 0 or more. Because right now you can use the catters and CADDRs and stuff like that to extract this exactly single identifier. The second that becomes a list of 0 or more identifiers, we have to make our solutions slightly more complex, which just takes the eye off the ball of what we're looking at right now. All right, does this make more sense now? So when you think about lambda calculus expressions, I want you to draw a line to something in your head that deals with methods in Java. Okay, that's what lambda calculus expressions are. It's a Java method with a method name. Okay, so this is the method. The method name might be, I might define blah to be a lambda calculus expression that just returns x, something like that. In Java, this is my method name. This is my actual method. So the method itself is its own animal, okay, that is only attached to that method name as if it's a variable. Make sense? Java doesn't differentiate those for us. We don't see the two sides of the syntax. With Java, we just say, oh, well, the syntax is return type, method name, parameter list, body. You know, we kind of just squeeze all that together. What the reality is somewhere under the hood, Java's creating a variable named blah and shoving into it something of type method. All right, but in Scheme, methods I mentioned before well, Lambda expressions are what are called first-class objects, meaning we can pass them as parameters into our functions. Java, you cannot pass methods into functions. Many languages have something called a closure, which allows you to fake. Well, fake's not the right word. Let's just say allows you to, well, it does. It allows you to pass functions into procedures, but it does it through this like specialty door known as a closure. All right. But by our definition here, that would be an example of a lambda calculus expression where x occurs both free and bound. So I break this down. This is this production. So production number 3 of our lambda calculus expression, this guy, which is 2 separate lambda calculus expressions which have nothing to do with each other. They live in separate scopes. Okay? So this is like looking at a Java program that has 2 methods in it. Those methods might have their own local variables, but they have nothing to do with each other. They don't cross, can't cross the streams, Ghostbuster style or whatever. Make sense? Okay, so 2 separate methods here. This guy has his own scope. This guy has his own scope. What's the scope? When I say scope, what am I talking about? I want to make sure that we're clear on this.
The area in which that variable is accessible.
Yeah, the variable environment associated with that function. So any variables defined here, any variables bound to this lambda calculus expression are not necessarily bound in this lambda calculus expression. Okay, and to Levi's point, the exact same variable that's bound here would absolutely not be bound over here, regardless. I mean, you might have 2 variables that have the same name, but they would not be the identical variables. You know, you could have a variable here bound by a variable x that equals 5, and you could have another variable over here bound by a variable named x that's equal to hello. You know, both named x, but 2 very different variables named x. Make sense? All right, so this is the production that we're looking at for the possible answer to this this question. What I did is I replaced the left production with that, our left lambda calculus expression with production 1, so just an identifier, so just x. So there's an example where a variable named x occurs but is not bound. That side makes sense? Okay, so that's a lambda calculus expression. I mean, if I just separate it, that is a lambda calculus expression where x occurs but does not occur bound. So it occurs free there. On the other half here, this guy right here, this is a second lambda calculus expression following production 2. This is an example where we have a single variable bound called x, and x also occurs in the body. Therefore, x occurs bound. Make sense?
So in the bottom expression, if you had x in parentheses but didn't have any number being passed in for x, it would occur free?
It wouldn't occur.
It wouldn't occur.
Yeah, in this example, x does not occur free or bound. It doesn't even occur. Yep. So that was your confusion. This is only a binding activity. Yeah. This guy, let's call it the body. So if we give definitions, this is the parameter list. This is where things are bound. This is where things occur inside the body. Make sense? Let me take this a step farther. So we're going to test that understanding. So Does X occur free or bound or neither in that expression? Remember what I just said a second ago. There's two separate sections. One section is where things get bound. Another section is where things can possibly occur. The body is where they occur. The parameter list, for lack of a better phrase, I guess, is where they're bound. This guy right here is the body of this parameter list. But within this body, we have production 2 of our lambda calculus expression. So we have another variable named x here, a more local variable named x, bound. Okay. Important thing here, though, is this x is not an occurrence of this x. This is a brand new variable named x being bound. So x still has not occurred. We have two x's that are bound. This x being a more local binding. So if x were used here, it would resolve to the most local definition of x, not the more global one. But in this case, since I had a y there, even though we see two separate bindings of x, x does not occur. Therefore, it doesn't occur free or bound. So if I had asked you to give me an example of a lambda calculus expression where x is bound but does not occur, this would be an example of it. Or where x does not occur free or bound, but that would be even simple. You just say t or something. It's like, I'm not even going to waste my time binding crap if I'm never going to make it occur. So that would be an example, just the lambda calculus expression t, where x does not occur free or bound because it doesn't occur. All right, kind of makes some sense? So we want to be drawing this connection in our minds to lambda calculus expressions are Java methods. Okay? And secondarily, the other thing we're focusing on right now is this idea of variable scope. So two very important things in programming languages, right? Reusable chunks of code and then remembering crap. And just in this example right here, we have two scopes. We have a local scope right here that is governed by a more global scope. And just like if I wrote a Java program that had a global variable named x, and then a method that had a local variable named x, and I used that local variable inside of that method, it would resolve to its most local definition. So something like this. If I had a public class hello, let's just say int x there. Void blah int x. Man, the scheme's not liking Java in here. Or racket. System.out.println x. If I do this, which x am I printing out here? This one. Yeah, we're printing out that version of x. Okay, because this version of x represents a more local definition than this version of x. That's why when we write constructors, so let's say this was a constructor called hello, we might say something, we can't do this, we can't say x equals x. Because that is setting the most local definition of x equal to itself. So instead, what do? I say this dot x. That allows me to jump this local variable environment and get to this version of x right here. Make sense? All right, so two things we're messing with right now are methods and variable environments. That's what we're focusing on. All right. And then let me just finish this up real quick. this would be an example in Java of a Java class or method here. If we want to split away from the whole Lambda or be equivalent to the Lambda thing, this is a Lambda calculus expression that we happen to throw into a variable named hello. Okay? In this situation, X does not occur free or bound because the body of this method, this is where stuff occurs. This is where stuff is bound. All right. So that should have been an easy quiz, shouldn't it? Out of curiosity, who got the quiz right or think they have a right solution? Now that you have seen this stuff. Understanding there's literally an infinite number of right solutions you could have written for this thing. I just showed you a pretty simple one. You at the very least had to have a situation where it occurred without being bound and another situation where it occurred with being bound. So I think I gave you kind of the easiest version of that, what I showed. Okay, so what we want to do today is we're moving into chapter 2. And I have given you a homework assignment. There are 42 questions. One question. And what we're going to do in class today is we're actually going to introduce. We're going to solve a problem in class that is similar to what I'm asking you to do for homework. Okay. I might even argue actually what we're going to do in class. Not argue. I think what we're doing in class is more difficult than what I'm asking you to do for homework. The homework isn't meant to be horrifically challenging from a logic perspective. It's meant to get you into this mode of specifying data in terms of constructors and predicates. Okay, so when we get into chapter 2 here, let me just flip forward a little bit. Oh, there we go. Okay, so we're dealing with this idea of data abstraction. Now, the first thing I'll say here is they reference this thing called interfaces. Your book has this specialty format. And you know how like there's the different programming choices you can do in Dr. Racket or Dr. whatever the heck the thing is called these days. And there's one of them, I think, for EOPL, Essentials of Programming Languages. It's like the book language or something like that. They introduced something called interfaces. I don't like using them. They're supposed to be more convenient. What it essentially lets you do is cut out the lambdas. But I really like working by keeping those things there. I think it's a reinforcement of how things work. That we're truly looking at something that is an unnamed function, an unnamed method. All right, so I won't give you any assignments that deal with the interface version of this, but understand, I'll point it out here real quick. When the book gives you some examples, let me fast forward here a little bit.
That was the homework, wasn't it?
Yeah, I passed it, but it's unrelated to this.
Oh, okay.
Yeah, see, like this, I'm okay with this. I like because it's defining it in terms of lambdas and that kind of stuff. Let me show you an example where it doesn't.
You're just talking about the define and then parentheses variable name or whatever.
Yeah, their specialty format.
You can do that outside of that EOPL.
Well, you'd have to write your own.
I think you don't have to. Maybe.
Oh, that looks okay there. Do they not have examples of that in here? That might be a good thing. Oh, no, this is it. Their data type stuff. This. I hate that. So they're defining functions here, but without lambdas. So they're defining a data type called LC expression, lambda calculus expression. And this guy has, it's defining it as a production. So here's our predicate for it. So it has it builds a predicate for you for testing if something is like that without us actually having to build it. Then we have multiple productions. We have our var expression, which is just an identifier. We have our lambda expression, so production number 2. which is our identifier, that's a bound var, as well as the body. And then we have our version 3, which is an app expression, like I mentioned earlier. But they've omitted all that Lambda crap. So while this might look cleaner at first, I think it hides too much from us, and I won't use that syntax. All right, so therefore I don't expect you to use that syntax on your homework, which actually comes out well because there's a lot of these things that are already done online. I think this is a pretty popular book that programming language classes use. So now, at the very least, you'll have to convert the solutions to the Lambda equivalents. So I do not like that syntax the book uses.
Looks fun.
It's absolutely helpful. I mean, but I think it's counterintuitive to learning the material. Yeah, it's absolutely better if you had to write this stuff day in, day out, and you were designing languages. It's not that the representation sucks, it just hides too much from us. I want us to see it.
So can we use it when we're actually writing languages?
No. All right. So the question you're going to have to, your homework question is 2.4. Okay, so in 2.4, you're basically going to be implementing a stack data structure. Like I said, it shouldn't be horrifically difficult. Some of you will finish it in probably 10, 15, 20 minutes. But what they really do is they talk about defining things in terms of these 4 functions. So they're trying to get you kind of focused into building constructors and predicates for testing data. We're dealing with data abstraction in this chapter. Okay, how do we represent data in a simplified form? Remember abstraction from 150 with the Albert Einstein picture dealy thing? Okay, so we're looking at how can we take complicated data, complex data, and represent it in a way that is easy for us to work with. All right, so we're going to start with this thing, which is very appropriate for this class. We're going to implement something called bigots. Like how doctors nice. It's like, what? All right, so the book, it is kind of actually a funny thing. Well, first of all, the book introduces this thing called unary representation. So like the number 5 would be represented as 5 trues. That's 5 trues is the number 5. That's a unary base 1. Base 1 is what it does. All right, but what we're looking at is let's see, where's the big num representation. All right, so what big num representation is it allows us to hold values in different bases. All right, so in some of my other classes, we've done conversions, base 10 to base 2, base 8, base 16, stuff like that, right? Typically, if we're thinking about big num, holding large values, it's advantageous to us to hold those values in bases larger than 10, right? Base 16 has a couple of perks. One perk is you can store the same kind of values in base, the same base 10 values in a smaller footprint. But what's the other perk of hexadecimal that those of you who took 325 learned? Why is hex good? Why is it very compatible with the core language of our computers, zeros and ones?
It was something about I can't remember exactly, but each place being a set of 4 in binary.
Yep, nibbles.
Niblets.
Yep, yeah, the niblets. Okay, so every block of 4 bits can be translated into its equivalent base 16 value, 0 to 15. So it allows us to actually move between hexadecimal and binary very easily. That's a convenience for us. Now we can represent large values, but still get them back to what the computer understands very quickly. Make sense? All right, so just more trivia knowledge there. But in any case, with our big num representation, which they say sometimes they're called bigots, I think, which is highly entertaining. Yeah, implement the 4 required operations for bigots. Then use your implementation to calculate the factorial 10, whatever. But let's give ourselves required things for bigots. Well, first let's understand what a bigot is. Like, doctor, would you like to? All right, so these are big integers. Instead of digits, it's bigots. Get it? Haha. All right. So they're saying that the number 0 is the empty list. Okay. We represent 0 as the empty list. We represent, well, here's as an example. If we have the decimal number 33, and I want to convert it into its bigot equivalent, where n is 16, I get the list 1, 2. So n is our base, 16. 33 converted to base 16 is the number 12. How do we do that conversion? If I have the, let me make this another quiz maybe. Google it. So 33 in base 10 to base 16. How do I do that math? Base 10. Should I make this one a quiz?
For tomorrow?
No, like right now. You guys should all have had this stuff many times. I've had you write programs to do this stuff. Absolutely. Yes, you have.
And that's why we forgot, because we used the program to do it now.
In 250, you write a program that does this. Hmm? Yeah, divide 32 by 16, or 33 by 16. Yeah, we probably called it, in 250, it was probably called binary to decimal and decimal to binary. Then we said base to decimal, decimal to base, where we looked at the generic aspects of it. So what do? We take 33 divided by 16. 33 divided by 16 is what? 2 with remainder. Oh my gosh. 2 with remainder 1. How many? 16 or 2 divided by 16 is 0 with remainder 2. Then you read it from top to bottom, so you get, actually you read it from bottom up, so you get 2, 1 as is the answer. So 33 in base 10 is the number 21 in base 16. They're representing the base 16 number in something called Little Indian notation, where it actually holds it backwards. So it's 1, 2, like that. Make sense? What's this?
It's a racist class.
We got bigots, we got little Indians. It's Endians, E-N-D-I-A-N-S. You can call them whatever you want. Still racist. You're going to tell me you grew up in Champaign with the Fighting Illini. Totally did.
It's also the most annoying bug to ever have to try to fix.
All right, so now that we've gone through that, every one of you in here has converted from hexadecimal to, or from base 10 to hexadecimal before.
I have never seen that before in my life.
Then you did not watch all the 250 videos that you told me you watched and did the class.
I feel like I did. I don't think I skipped any. Maybe there was a day missing and this was the day.
Maybe it was one that got
where
reported
you
for
taught, you
copy.
taught it to us and then you put 2 questions on the
Nah,
exam.
I always do this. I mean, I typically am I do number conversion stuff in almost every one of my classes. We do it in 200, we do it in 250. I've given quizzes on it all over the place.
Yeah, 'cause I always fail those.
Yeah. Yeah, I don't care if you fail it. I'm talking more that you've seen it. This should not be the first time when you're in 470 that you've seen how to convert from decimal to hex. Okay?
It is.
If you are, you need to get your head checked.
He's telling me things are wrong, I just don't listen.
You haven't had 325 yet?
Me?
Yeah.
That's next semester, isn't it?
Some
I
of you
feel
probably.
like for us, you did it later than 250, but then you started
No,
doing it.
I always do that assignment in 250.
Well,
What is
okay. I think as a program you did it later, because when we actually wrote it as a program, we did it later. When we did it originally, you did teach it to us, I know.
I think we wrote it for.
That program usually comes well before midterms in 250
I don't know.
because it deals with string manipulation stuff. Like I think I'm probably giving that program in 250 this semester, either next week or the one after.
Give it to the
Well, I've already had that class today. All right.
doesn't matter.
Regardless, this is what we're
Let's
producing.
find out. I have all of my 250s.
Make sense? Shut up! All right, makes sense what we're producing? All right, so take a decimal number here as well as the base we want to convert it to, and we're going to turn it into one of these guys. A list containing our numbers in little endian form. All right. See, she lucked out. She told me she was going to be late, so she gets a pass on the quiz. Everybody failed it. So you're probably going to be the only A. Woot. All right. So let's go here. Back to the book here. All right. So what I want to do is I want to bounce back up here and look at what they've done, because they've given us unary representation as our example. Because they mentioned that we have 4 functions that we want to produce here. Okay, 4 functions we're going to produce here. So let's understand how unary representation is going to work and how those functions were defined in terms of that. Then we can take that and expand it to do our bigot implementation. Okay? So again, unary representation is a list containing a number of trues equal to the number it's representing. It's kind of like base 1 representation. The number 3 would be a list of 3 trues. All right? So 0 is the empty list. A number plus 1 is going to be true followed by a unary number. So we're going to say that this is a unary representation. Unary representation, that's the name of our grammar. Okay? So they've defined 4 functions here. One function, this is a constructor. Okay, again, we're thinking about building things in terms of constructors and predicates. We have a constructor to construct the unary 0. All right, the unary 0 is going to be a lambda procedure that takes no parameters and returns the empty list. Why? Because the unary 0 is the empty list. Now, why did I actually have to put a method in here instead of just return the empty list? Because it's a constructor. Constructors are like methods, but they might not do anything, right? So this is the no argument constructor that returns the empty list. That's what this guy does. So kind of consider that constructors are functions that may or may not do something. Well, constructors are functions that do something. What they do might be very minimal. In this case, this guy boils down to the empty list, but he still is a function, which means that 0 can be applied to something else. All right, we don't just say 0 and get the empty list. We take the list containing 0 and 0 parameters. So our third production of the lambda calculus expression, giving no parameters to a function stored in a variable called 0. And when you apply nothingness to that, since this guy takes in no parameters, it will boil down to the value of 0 in unary representation, which is the empty list. Make sense? All right, so they're taking a really simple example to try to talk about something that's kind of abstract-y, hence the name of the chapter, data abstraction. All right? So this is our constructor for constructing the unary 0. Now, what's this guy, Abe? Predicate. How do you know? Without even looking at what it does. You know it's a predicate because our naming convention says whenever you put a question mark in the end of it, that's probably going to be a predicate. Okay? or you're Pebbles and you're just randomly typing stuff. How'd you do in the quiz, Pebbles?
He's regretting not throwing the 5.
Yeah, I really wish I did that.
Really? You think a $5, if that $5 buys you an A in that quiz?
$1 for every point, right?
Yeah, point. Okay, so what percentage would you like? You haven't noticed yet, quizzes are usually graded in 30%, 50, 70, and 100. Every now and then I throw some 90s in there if you're like close to 100 but still a little dumb. So 70 is like pretty good but no. 90 is like basically right but not quite. 100 means basically right.
What's right?
Well, just in general, like I mean,
No. What's being like?
if I'm giving a quiz, I'm not looking like if you forget a curly brace or something like that. I'm not going to drop you to a 70 on a programming quiz because you.
You did that to me at Hello World. So.
Well, that was because they had to write it perfectly. That's different. And actually, you dropped you to a 30. You just got attendance points. 30 means you were here and your name ended up on a piece of paper.
I don't know as far as I got that far.
All right. That's how I differentiate people who skipped from people who took the quiz and bombed. Okay, so in any case, this is our predicate for testing whether a value is 0. So this predicate, again, is going to be a function. It's a function that takes in a single parameter and asks whether or not that's the empty list. Right? That's what that function does for the unary operation. Successor. Okay? Successor means next value. So given a unary value, give me the next value. So the unary 1, well, let's say the unary 0 is the empty list. The successor on that would be a true concatenated onto the empty list. So cons true onto the empty list, giving us the list true, which is the unary 1. The successor of the unary 1 would be the unary 2, 2 trues. Successor of the unary 2 would be the unary 3, 3 trues, so on and so forth. Okay? The predecessor would be taking everything but the first, the coulter. Make sense? Successor, add a true. Predecessor, remove a true. All right? But this does not take into consideration going negative. So unary is 0 or greater. All right, so if you try to call predecessor on the on something that's 0, you're going to have real bad results real quick. All right, that makes sense? These are our 4 functions. All right, so going down here to our big num. Okay, so in big num representation, numbers are represented in base n for some large integer n. Okay, so for example, base 16 would be our hexadecimal thing. The representation becomes a list consisting of a number between 0 and n minus 1. So base 16, the legal numbers are 0 to 9 and A through F. Base 10, 0 to 9. Base 8, 0 to 7. N minus 1. Get it? Is that the first time you guys have heard that too? No, it should not be. 470 and don't know how to convert from hex to. Yes, I know, and I also have a very good memory. Huh? So you're saying it was because it was a long time ago? But don't I do number conversions like in almost every class?
We do something like this.
We learned 250 and then like 325.
We know we did it, and yeah, it was 200.
Well, 325 we spent a long time doing conversions. So if you've had 325 and you think you've never learned conversions, you missed something.
We did it.
There was a large swath of that class, like a month. Huh?
The only thing we did since 200 was take a quiz on it last year.
But you haven't had 325 yet. So it's just where you're at in the curriculum.
What is 325?
Architecture, organization architecture. Is that next semester? next fall. I teach it whenever it is. It shows up on my schedule. Well, you'll definitely learn about number conversion then, but I do it in 200, I do it in 250, I do it in both
We
classes.
didn't do it in 250.
Yes, we did.
There's no
In
way.
the homework.
Are you looking at your homework assignment for 250?
Yeah,
It was
I
the
had
200 homework assignments.
I
So
did
Angel, we
250s
only
too.
turned in like 7.
Oh, you're looking at your old assignments.
Yeah, I have everything in Dropbox.
Yeah. It was definitely in there.
I just remember in 300.
300, I think we did
talked
too.
about it during the class.
During 300, yeah, but it's 300 is the extension of 250.
We should have this exact same conversation then, yeah.
But this is 470. I mean, basically, you should know everything. So this is the highest numbered, well, 490, I guess, is our highest numbered class.
491.
It's true. All right. See, that's an example of successor. 490 plus 1 would be 490. All right. So, in any case,
List of 490 truths.
this representation makes it easy to represent integers that are much larger that can be represented in a machine word. For our purposes, it is convenient to keep the list with least significant bigot first. It's a little endian. We always put the least important bigot in the front of the line. That way things get more and more bigoted as we... Somebody takes this lecture out of context. It's like, Lippmann was, I mean, you just got to hear this.
Your white Jew is just.
All right, so,
Your YouTube account's being watched. You gotta watch it.
who?
Your YouTube account will really get banned on this one.
Something. All right, so for our implementation, we're going to assume n is 16. Okay? Just because we don't want to focus on supporting a zillion different bases, although 16, 22, 28, all those bases are identical to how we calculate it. But we'll just do it for base 16. All right, so so we want to first define the constructor for 0 in base 16. So if I convert the decimal number 0 into the hexadecimal number 0, what's the equivalent? How do I convert that? Zero from base 10 to 16. We're going to take 0, we're going to divide it by 16. How many times does 16 go into 0? 0 times, with the remainder 0. We know that since we have a 0 here, we're done. The answer is 0. So, that is the bigot representation of... Val just walked by. I think she walked by right when I said the word bigot. That is the bigot representation of 0, assuming we're dealing with n is 16. Base 16 numbers. All right, so we're going to go ahead and write that. So we're going to define 0 to be a lambda that takes in no parameters and boils down to the bigot 0. This allows us now to create our first bigot.
They've been created for a long time.
Realistically, we probably should reference them as bidgets, but
I'm not sure.
since that goes by, digit, bidget, but this is so much more controversial.
No, I feel like you could slip off the other one pretty easy.
Yeah.
Yeah, I think so too.
Am I missing a phrasing? Am I?
You're missing something.
Wouldn't necessarily call it a phrasing. It's
It's just a word.
You mean I can take, instead of saying bidget, I could say bigot? Or I can go worse?
there's a certain expletive which may be easy to say if you're saying bidget.
Just say fidget 10 times over and see if you can.
Just try it.
Repeat that in your head 10 times and see where you
It
get.
doesn't seem like it's that close. It's the G rolls you into it?
Yeah.
Oh, all right.
No, I don't agree.
Yeah, I don't think so.
Fidget, 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 fidget,
All right, shut up. All right, so now we want to write our predicate. So predicate is define 0. This guy's going to take in a bigot. This guy's going to take in a bigot. And it's ultimately going to boil down to true or false whether or not that bigot is the bigot 0. All right, so how do I write a procedure, a lambda here, that takes in a single value and a single bigot? So it's guaranteed to be a list of 0 or more and determines whether or not it is indeed the bigot 0. We know that all bigots must have at least one number in them. So 100% of bigots have a car. Make sense? Whoever wrote this book. Oh, it's like, that's stereotyping. How do you know all bigots have cars?
Of course some of them take the bus.
All right, so would you agree that all of them, what do you mean them? Would you agree that all of them have a car? The smallest bigot we can have is the list containing a 0. You got to roll with me here, people. We got to get through this. Okay? All right, it's a list containing just a 0. So the car of that list would be a 0. And the cooter of that list would be the empty list. All right, so we would return 0 if what is the case? Well, it's going to be a lambda. That's going to take in a bigot as a parameter. Okay, and this guy's going to return and. Have I done just EQ is what we've been using? Okay, but actually we can use equal in this case. So and car of bigot is 0. Or we can actually use the 0 predicate if we wanted to, but whatever. So the car of it is a 0, and null cooter. Just kick this down a line. Just give us a little bit more structure. Something like that. So if I pass this guy, if I said 0 question mark 0, oh, 0B. Can't call it 0 because there's already a 0 in the language. There's our true. The constructor 0 for our bigots boils down to true when we pass it to our predicate for our bigots. Did you see something about boiling bigots? Well, I should probably pack up my desk. Yeah.
Every time I try to run exactly what's up, I keep getting expected at least one variable after lambda without none.
So you mean when you every single time you run something, it's almost like what I have up here.
Do you have parentheses around bigot? Yep. No, it's like from the first expression. Like the,
Oh yeah, the lambda parentheses parentheses where you don't have anything there.
yeah.
I mean, because you're in the, what language are you under?
Oh, you have intermediate.
Oh, right.
Intermediate student with lambda.
We're good? All right. So, in any case, now we have our first two things. So, the constructor for making our 0 bigot and our predicate for testing for something being 0. Next, we need our successor. That is taking a bigot and adding 1 to said bigot. One-upping the bigot is the, I guess at this point we should just roll with it, right? All right, so how do we do that? So for instance, if I take in, let's look at the pattern here. So 0 base 16 to a 1 is what? How do I add 1 to a base 16 number? Okay. Let's say I have the number A. How do I add 1 to A? What do you think? Because for example here, I should be able to say, I should be able to say something like successor 0, and this guy should spit out, in this particular case, the list 1. 1 greater than the bigot I passed it. Make sense? But now when I get to 9, and I say add 1 to it, it should not be 10. It should now be A. Once I get to 15, so I'm at F, and I add 1 to 15, what do I get? You get 1, 0. Actually, in this case, it would be 0, 1, right?
Yeah.
That list, because we're in little endian form. Then it would be 0, 2. We're adding 1. So I have this. Let's write the bigoted format of our first several numbers. So there is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So let's go 0, 1, 2, and then let's go 9, A, B, F, 1, 0. I'm sorry, 0, 1. 0, 2. 0, 9. 0, A. So on and so forth. Make sense? So how do I do that? How do I do that math? I'm always taking, so when I got to here, and this was my representation of the bigot, what number did I add 1 to? The second one in the list, the last one in the list, okay, because of the order it's being stored in, right? So really, what do I need to do? I need to have the ability to reverse a list, take the car of that list, add 1 in base 16 world to that car, then cons it back onto that list, and then reverse it. Okay, so we need to have the ability to reverse a list first, so we got to write that. It does already exist, but
Obviously, that's not in our toolbox. So.
no, it should be. Why not?
No, it is.
Yeah, why not? So reverse 1, 2, 3 will give us 3, 2, 1. So now you can use the built-in function called reverse. Because I think we could write reverse if we had to, right? So might as well focus on our language construct stuff. All right, so we're going to reverse the list, take the car off, add 1 base 16 to the car. All right, and then what are we going to do with that value? We're going to cons it back on. But what if my value is this? So let's say I had the list, let's just say 1F. First thing I'm going to do is I'm going to reverse it, so that gets me F1. Then I'm going to car it, that gets me the F off that. And the cooter would be the list 1. Now I'm going to add 1 to F. What is 1 to F? Should we result in 0? Should result in 0, 1. Right? So this guy actually will become 0, 1. That make sense? If I created a list out of the car, and then I called successor on that, can't I define successor in terms of itself, recursively specified data, rather than manually add 1 to it? So when I have singletons like this, an F always becomes the list what? 0, 1. That's a stop case for us, right? As soon as this guy gets back up to an F and I reverse it, giving me F0, and I take the car of that and put it in the list, and I get that back, and I turn that into 0, 1. So I took the car of that guy, so I got 0, 1 off of it, and I'm putting it back onto a 0. And I want these guys to go back together. How do I put them back together? Append. Now we're putting all these little tools together. So 0, 1, the list 0, 1 appended with the list 0 will give me the list 0, 1, 0, which I will then reverse and end up with 0, 1, 0. So is 0, 1, 0 1 greater than 0F? It is. 0, 1, 0 is 1 greater than 0F. So successor is going to be a lambda that takes in a bigot. And I need to reverse. I know that bigot's going to have something in it, right? It's got a soul, maybe. So I need to reverse it, then car it, then list it, then call successor on that. But successor is going to boil down to a couple of things. We know a stop point for us is in a cond. So if I say that the list I'm looking at, if I'm looking at the list F like this, then how do I check to see if I'm looking at the list F? Because only when I'm looking at F does the 1 list become a 2 list with successor. So we're going to say EQ question mark car of reverse. Let's see. Reverse bigot will reverse it. We take the car of that. That should give us the F. Well, we're going to be in a whole lot better shape here doing it as a let, but let's just keep going. So reverse take the car of that if that's equal to an F. So we just committed ourselves to always using uppercase letters for our representation.
I think you need another parenthesis after bigot.
Oh, yeah, to close that. So if that value is equivalent to that F and null, it's not really what we want. We got to use a let here, otherwise we're going to drive ourselves insane. So I want to store that value. Otherwise, we're going to have so many parentheses inside of parentheses. So I'm going to let curval be equal to, we're going to reverse our bigot. Then we're going to take the car of that reversed thing, and we're going to put it in a list. All right, so curval will hold something like this. If this is our bigot, curval will end up holding the list 1. Reverse it, take the car of it, stick it in a list. That's what curval is equal to. Now I have a variable named curval I can ask questions about without having a zillion things in parentheses. So now I'm going to get into the body here of our let. So we're going to do a cond. And we're going to say if, so and the car of curval, if that guy is equal to an F, and null cdr of curval. Okay? So if we're looking at the list only containing an F, that's what this says, then I know I need to boil down to the list 1, 0. Not 0, 1, but 1, 0, because I'm going to be re-reversing it later. All right? So successor for the F list is the list 1, 0. So that's it for that cond. All right? So that's when we jump to a 2 list from a 1 list. If we aren't at an F, then I need to add 1 to whatever that value is. That means it's either a 0 through 9 or an A through E. So that would be here. But what am I doing with this value? Where does the append come in? First time through, I'm going to pass it 0. I'm going to ask, is this guy the F list? He's not. So if he's not the F list, what do I need to do? I still need to reverse him, right? And really what we're doing is we're not asking if this whole bigot is the F list. What are we asking? We're asking if the car of the reverse, the list of the car of the reverse is the F list. Only the last bucket of it. That's the guy we're actually adding 1 to or not adding 1 to. Okay, so this guy right here doesn't just boil down to that list. It boils down to that list tacked onto the list we removed the F off of, and then reversed. Make sense? So let's write that. So we're going to say we're going to append the list 1, 0 onto what? We want the rest of our list. Everything not including the last element. So that's the cooter of the reverse of our, well, actually, we could put this in another variable, but whatever. Big it, like that. And then we're going to reverse that. Yep, good. So we're going to reverse the list returned by appending this list onto the cooter of the reverse of the other list, which will give us that guy. All right. Oh, we're out of time. All right. So I'll save this. Like I said, your homework assignment is substantially easier. Okay, so your homework assignment is 2.25. We'll finish this next time. I think you're seeing the direction we're going with this. 2.24. Where's the book here? It deals with stacks and stuff.
It says do it like the way they said in the example above, like that. So do you want us to do that, or actually do the stack, like make the stack?
I think they say except implement, consider the data type of stacks of values with an interface consisting of the procedure empty stack, push, pop, top, and empty stack.
But then it says write a specification for these operations in the style of the example above.
Yeah. So you're going to create a constructor for empty stack.
Okay.
You'll create something for pushing,
Okay.
popping, looking at the top, peek, and then the predicate for checking to see if something's the empty stack, which would be the empty list.
So
Make sense? So instead of writing successor and predecessor and those guys, you're going to write those functions instead. So that's what they mean by in the style.
So when you're
above.
doing pop, are you returning color or how? Because
You can decide. You can decide if you want your. The easy way to do it would be the car. So
you're popping off the list, so somehow you have to return that stack still without the first variable, right?
to pop returns the variable,
Pop returns the first one.
but you're not changing this.
You should, yeah, because what else is popping?
You're only changing if you put it back in the variable. So if you have a stack with 1, 2 in it and you pop it twice, you're going to pop off the 1, you're going to pop off the 2. So it does boil down to a lesser stack, like you're saying, but unless you put it in you're not returning it, it just boils down to that value.
Yeah. What?
You want to know how do you deal with both sides? How do you
Yeah.
if you have the list 1,
how do you
2,
boil down
how
to
do you get the
variable
1
and
and then how do you
stack?
also get the list 2?
Right.
All right, well, so you have to decide, does my pop return the resulting stack
Right.
or does my pop return the value that's at the top of the stack?
Well, otherwise you're just doing top twice.
Realistically, you probably want it to, well, that's true. That's true, you would be doing top twice.
Yeah, so you're probably just taking everything after the first value.
You probably should boil down to whatever the stack is. This thing's all about constructing and manipulating values.
Right.
Okay, so when I pop something off a stack, the result will be a new stack with the first element removed.
Yeah. So you're just essentially taking the cooter.
Correct. Assuming
Then-
you build your stack that way.
Okay. Yeah. Then I'm done. So I thought it was just either I thought I was missing something or something. It was just